All right, in this lecture we're going to start analyzing the unsteady performance of our aircraft. Now if you recall looking at the performance roadmap, we focused so far on static performance or performance of the aircraft in level and steady flight. In this case looking at primarily on-design performance when the aircraft is in cruise, but also quasi-steady performance, primarily where the aircraft is steady but unlevel, both for rate of climb and gliding flight. I know this obviously is very important, but it overlooks some of the very important aspects our aircraft is going to be in when it's not in these steady maneuvers. So when we're looking at dynamic performance, we're primarily interested in things such as takeoff, subsequent landing, and then turning flight or maneuvering. Now these are going to tie into the maneuvering and control of the aircraft and really factor into how we design those components, not only in order to be able to keep our aircraft stable, but also to put the aircraft into various maneuvers and be able to control it throughout the entire regime of flight. Now, sometimes this will be for flying off design. So if you want to take that aircraft out of that on design cruise portion of flight that we've designed for, but the aircraft is still going to be flying level and steady. As an example here, both the V-22 and the F-35 are obviously not flying at their on-design cruise point, but they're also flying at a constant velocity and a constant altitude. In this case, they're deploying control services and controlling their aircraft in such a way to be able to maintain the attitude and the speed in that off-design point in their flight envelope. What we're really going to focus on, though, is maneuvering aspects of the aircraft. That portion of the aircraft flight envelope where you want to be able to transition from one attitude or one velocity to another attitude or velocity. And obviously, this maneuvering portion of our aircraft is an extremely important piece within the design aspects, and as such, so we'll often find requirements for these maneuvering values or specifications built into the RFP, such that many times you'll have to meet certain maneuvering requirements for the aircraft in almost all aircraft design cases. We're not designing the aircraft just to be able to fly level and steady. We have to think about how the aircraft is actually going to get to that point and how it's going to maneuver around many obstacles it's going to encounter within its maneuvering envelope. As an example of that would be 737 MAX. So when we think about the design considerations that went into this particular aircraft, we have the normal things such as lift is equal to weight, and then we have a tail force that is being generated by our horizontal stabilizer in order to be able to counteract the moments that are generated. Now, in the cases of the 737 MAX, one of the issues that has led to the problems that it has experienced is due to the large size of the nacelle. It created a much larger force during high angle of attack maneuvers, particularly during climb out. So as this nacelle force was creating an additional moment that the tail would have to account for, this was built into the control system, the NCAS Maneuvering Control Augmentation System. So it would take information from sensors, airspeed sensors and angle of attack sensors in the nose, send that to the control system, which would then override commands from the pilot in order to be able to keep the aircraft stable during these high angle attack maneuvers. And we'll come back and talk about this a little bit more when we talk about design of the control systems and control surfaces on the aircraft. Now, one of the things that really drives analysis of the structural design of the aircraft is really the unsteady forces. We've already looked at the forces in level and steady flight, but when we look at the forces acting on the aircraft from its varying attitude, accelerating flight, And then more importantly, when we start to deploy control surfaces, things such as ailerons, elevators, rudders, flaps on the aircraft, that's going to impart forces acting on the structures of our aircraft. When we encounter things such as gusts, when we take off or land, it's going to be these dynamic forces acting on our aircraft that are really going to determine what the overall structural design of our aircraft is going to look like. What are those limits and what are those requirements that we're going to see? So we can look at all the sources and locations of our typical aerodynamic loads that we're going to say encounter in a typical aircraft mission, and all of these are going to then be imparted on the structural design requirements for our aircraft. So it's really analysis and determination of these unsteady loads that are going to impart the requirements and really inform the design of the aircraft structure. So before we can get to talking about the aircraft structure, we really have to talk about the generation of these unsteady loads first. Now to do this, we go back to our equations of motion that we derived earlier for climbing, accelerating flight. So in this case, we're changing not only the attitude of our aircraft, but also the velocity. So we are unlevel and unsteady. And in this case, we end up with two sets of equations, really a pair of equations that's acting perpendicular to the direction of flight, which is really balancing centrifugal forces based along that curvature flight path that we have with what our instantaneous forces are going to be acting on our aircraft, and then the accelerating forces along the parallel to the direction of flight. So this will be the change in our velocity or instantaneous velocity acting on the aircraft, again as a function of those unsteady forces acting on our aircraft. So we can look at both the left-hand side and the right-hand side of these equations and think about all of these terms: velocity, lift, thrust, drag, and even weight as all being functions of time. Now for most of our analysis, what we're really going to be looking at is a instantaneous analysis. We're going to assume that these forces are constant at one point in time. So even for sustained flight, when we look at this for banking maneuvers, where we're going to assume that our forces are acting sustained in flight, to get to that point, we're actually going to have to change these values in order to be able to impart that motion that generates these unsteady forces acting on our aircraft. So we take these, and this really then generates three sets of equations, two for the forces acting perpendicular to the flight path, and then one acting parallel to the flight path. And then this allows us then to calculate not only those unsteady forces on the left-hand side, but also determine the requirements for the forces on the right-hand side of the equation. Now these are overly simplistic, obviously, but they're going to be good enough for what we need to do in our particular scenario. So first we'll look at banking flight maneuvers. In the course of banking flight, as we're starting to bank our aircraft, what we're going to be doing is in a sustained fashion, increasing the angle of attack on our aircraft such that we're generating now a higher angle of attack and then a higher lift force. Now, for this particular maneuver, what we're going to be doing is keeping that angle of attack constant, such that once we've banked over at our bank angle phi, that lift acting in the vertical direction is going to be equal to the weight of our aircraft, or lift times the cosine of phi is going to be approximately equal to the weight of our aircraft. So now we are maintaining altitude. Now once we've banked, since we have a force acting in the horizontal direction, that's going to change the direction of our aircraft. And if we do this in a steady, sustained fashion, this is going to lead our aircraft to essentially travel in a circle. So now we're going to be orbiting around a single point, a distance r away from the aircraft. So we can balance that force with the centrifugal force acting on our aircraft, essentially wanting to push our aircraft off away from that central point that we're orbiting around. And we can kind of think of that aircraft, being swung around on a string, where that tension within the string is equal to that centrifugal force, the mass of the aircraft times the velocity squared, divided by that bank radius, which is then going to be equal to the force being imparted within that direction. So it's that component of lift that's acting in the horizontal plane, L times sine of phi. Now, once we have these basic equations, then we can then determine what that bank radius is, and essentially solve for that bank radius. But one thing we want to do is pull out that lift. We don't want to know or have to calculate how much lift the aircraft is actually generating within that banking maneuver. We want to make this calculation independent of that. So what we're going to do is define the load factor, in this case N, which is the amount of lift that we're generating divided by the weight of the aircraft. Now, as we'll see, this is going to become a really important structural design requirement for our aircraft. But it's also related to the maneuverability of our aircraft. So this load factor becomes extremely important in terms not only the capabilities of the structural limitations of our aircraft, but also it's going to determine how maneuverable our aircraft is going to be. So once we've defined this, we can insert this value back into the equation, centrifugal force being balanced by the lift force acting along that horizontal plane of flight, and then solve for that bank radius. So in this case, the bank radius is just equal to the velocity squared divided by gravity times the square root of n squared minus 1. Where's gravity come from? Well, notice we have mass defined in our equation as part of that centrifugal force. Now I have the load factor W being defined as lift divided by weight. So we're replacing weight with mass times gravity. So once we substitute that back into the equation, we're left over then with gravity. Now once we have that radius calculation, then we can calculate the bank rate, which is just the velocity that we're traveling at divided by that bank radius. So one is going to tell us how large that turn is, what's the diameter of your orbit that you have, and the other is going to tell you how long it takes to make one full circle around that particular orbit. Now, as we've mentioned before, if we really want to be able to do this in a what we call a coordinated turning fashion, since we are generating more lift on our aircraft, that means we have to fly at a higher angle of attack to be able to do this as part of that maneuver. And to increase our angle of attack, we have to deflect our control surfaces acting on our tail. Now, what's that going to do? We're creating more lift, which means we're creating more induced drag. We're also creating more drag on our tail, which then means we have to increase thrust to be able to go into this banking maneuver. So it's not just as simple as deflecting our ailerons and rolling over. We're also going to have to pitch at the same time in order to be able to do this in a coordinated fashion. And to do that, we're creating more drag, which requires more thrust. There's a lot going into this when we start to think about how this banking maneuver actually happens. We're not going into the details, but we just need to be aware that in order to make this happen, there's a lot of stuff going on our aircraft in order to go into this coordinated flight maneuver. Now we can relate the capability of the bank angle directly to the load factor that our aircraft is able to sustain. So as we're increasing that bank angle phi, we can actually write that in terms of the load factor N that we've already defined, from our previous slide. So for example, if we're going to bank at an angle of 45 degrees, that means our load factor is going to be equal to 1.4 times the weight of our aircraft, or 1.4 Gs. So we're going to be creating 40% more effective gravity acting on our aircraft, or at least that's what the passengers and pilot are going to feel, as well as the structure of our aircraft. So now our aircraft is not just going to be designed to be able to carry the weight of our aircraft, it has to be designed to be able to sustain 40% more weight from a structural standpoint on the design of our aircraft. And then you can easily take all this way up to a 60-degree bank, 70, 75-degree bank to determine, what the total G loading is going to be on your aircraft. And so you can begin to see where this is going to start to come into the structural design requirements or elements of our aircraft. Now, the banking maneuver that we looked at was a sustained maneuver. We can also do this for pull up and pull down maneuvers as well. The equation is actually a little bit simpler when we start to look at it in this standpoint, and we can solve for both a pull-up radius as well as a pull-up rate. You'll notice the resulting equation is also a little bit easier. So the process to get to this equation is really the same route, but now we're looking at the forces acting along a different direction rather than acting within a plane parallel to Earth. We're now looking at the forces acting perpendicular to the forces of gravity. In this case, however, since as you're changing the attitude of the aircraft, you're going to change the direction of those forces as well. We're only looking at this in terms of an instantaneous pull-up maneuver rather than a sustained pull-up maneuver. Now, if we start to think about what the forces look like when we're doing these maneuvers on the aircraft, we can start to get a better idea about how this is really going to impact the structural design of our aircraft. So think about that lift distribution acting along our aircraft wing in level and steady flight. Now imagine that our aircraft is going into a banking maneuver, or it can be going through a pull-up maneuver as well, where we're increasing the angle of attack in order to be able to generate lift forces in order to be able to execute that particular maneuver. But in a banking maneuver, once we've banked over, first we have to think about, well, how does our aircraft actually get there? Well, we're deploying control surfaces in this case, the aircraft is flying towards us, so on the port side we have our aileron down to generate more lift, and on the other side we have our aileron up to generate less lift. So our resulting lift distribution is going to look something like this. First off, we know the overall lift distribution for a sustained banking maneuver has to be overall larger. So the area under this curve in the bank is going to be much larger than the area under the curve in the level and steady flight. So we're generating more load acting on the overall wing. Also, we have an uneven distribution. So the loads now along the wing not only are greater, but they're also uneven. So we have a higher angle of attack, the way to do this. We're generating more overall lift, and our load factor now is going to be greater than 1 in order to be able to execute this. So this really then becomes a design limit for the structural design of the wing of our aircraft. So we're going to look at this and think about a requirement and say, well, I want my aircraft to be able to bank at 45 degrees. If you can think of that as like a maximum bank angle or design requirement for your aircraft, then that's going to determine the wing structure for this particular maneuver. It may not be the most severe the aircraft is going to see, so you have to look at all different phases of flight, but this now gives you one design point that you have to make sure that your structure is designed around. So this leads us then to our Venn diagram. And the Venn diagram, just as the name implies, is velocity versus load factor. And you can really think of this as a structural flight envelope for your aircraft, where as you're increasing velocity on the x-axis, you may be increasing or decreasing load factor then on the y-axis. And it's the limits in terms of minimum velocity and maximum velocity, and then minimum load factor and maximum load factor that's going to determine your maneuvering capabilities for your aircraft, which is then going to dictate what the structural requirements for your aircraft look like. So the horizontal axis is pretty straightforward, right? In terms of velocity, this maximum velocity is really going to be determined by the maximum velocity capabilities of your aircraft, your maximum thrust versus the required thrust or the amount of drag that your aircraft is generating, but it's really the vertical load factor that's going to determine the maneuvering capabilities for your aircraft. Because we know already that that goes into both the bank angle and the pull-up capabilities for your aircraft. And so the maximum value of your vertical component in this is then going to determine what that overall capability is of your aircraft to be able to pull this maneuver. And this is really going to be, again, kind of dictated in two directions, both by the specifications of your aircraft, how maneuverable do you want it to be, and then your structural design capabilities. What did you design it to be able to structurally withstand with any given maneuver? Now there are a couple of bounds for this. On the left-hand side, we're going to have the stall locus for the aircraft. So that in-max curve is really just going to be determined by the wing loading, the dynamic pressure that you have at any given velocity and altitude, and the maximum lift coefficient for your aircraft. The right-hand side then is going to be determined by the maximum velocity, the maximum capable sustained velocity for your aircraft. So you can go back to that Vmax equation and solve for level and steady flight, assuming Nmax is equal to 1, then to determine what that velocity is going to be and provide you with some bound for that particular max speed. Now, the most important point on our Venn diagram is going to be this corner speed. And you can kind of think of this as the bounds between your aerodynamic limits on the left-hand side and the structural limits on the upper bound of this. So where these two meet gives you essentially your best maneuvering point. It's where you're flying the slowest, and so if you go back and look at your bank radius and then the bank rate that you have, that's going to give us your most maneuverable point at that highest sustained maximum load factor that you have. And again, you can think of this, if you look at the corner speed, it really just is the stall velocity, but now at that higher load factor above the level and steady load factor of n is equal to 1. Obviously, anything that we're going to design for our aircraft has to be able to sustain a load factor much higher than n is equal to 1. Otherwise, we'll never be able to get off the ground. Now, there will be requirements for our Venn diagram that are going to typically be dictated by the specific mission that we have. For civilian aircraft, these are going to be given by the Federal Aviation Regulations, or FARs. So based upon the category or class of aircraft that we have, as well as different points along that Venn diagram. So typically, things such as general aviation, a transport aircraft, they're going to range in the around 2.5 to 4 or so in the positive load factor, and the negative load factor, where we essentially are looking at pull down maneuvers, where now we have negative G loading acting on our aircraft, is going to be somewhat lower than that, because we don't expect to see those same types of maneuvers as often or as severe during our typical aircraft operating flight envelope. As we go to higher values, things such as aerobatic or fighter aircraft, obviously we can have much higher G loadings. Even with modern aircraft, maybe as high as a positive load factor of 12. As I mentioned, those FARs are going to typically dictate what our load factor is going to be, and in this case it's a function of the weight, primarily because what we're going to see is as we have larger aircraft, they're going to be less susceptible to gusts, and they're also going to tend to be less maneuverable. And so you'll have a limit of a 2.5 on the higher side. So most of our large wide body transports airlines are going to be designed with a maximum load factor of 2.5. Again, that may not sound like a lot, but if you think about it from the design standpoint, that means that your aircraft has to be able to withstand 2.5 times the maximum takeoff weight that you're designing your aircraft for. So that's still, pretty stringent in terms of designing the structure of your aircraft. And this again has to be that minimum value. You're typically going to design over this as well, with a margin, say, of 25%, in order to be able to make sure the aircraft is not damaged as you're flying up to this limit. As I mentioned, one piece of this is the actual gust loads. You have to be able to design your aircraft to withstand turbulence that you might encounter during flight. Without going into too much details of this, these are primarily going to be designed based upon sharp penetrating gusts, meaning that you'll have a sharp edge or a step gust that you'll encounter on your aircraft, where it's going to very suddenly, change not only the velocity but the angle of attack the aircraft is particularly experiencing at that given point in its flight. And so these gust lines will then be exhibited by looking at both from the level and steady flight point to the maximum bounds that you have in your VN diagram. You will have a range of different maneuvers that you'll be looking at. We've looked at pull up, but you'll also have pull down, pull over, and vertical maneuvers as well. Each of these can be calculated assuming that the aircraft is encountering this at its instantaneous point in flight. And this essentially provides you all the bounds of your aircraft. You can imagine that if your aircraft is going through a loop, it's going to go from a pull up to a vertical to a pull over maneuver as it starts off with that loop until it goes all the way through and returns back to its starting point. So you can see the variation in both the turn radius and the turn rate throughout that entire maneuvering portion of its flight. Now, once you do this, then you can start to generate, plots that allow you to analyze the behavior for these different maneuvering factors across a range of different load factors or values of N throughout the entire flight. As you increase, the value of load factor that you have, you'll asymptote to a value that's going to be a function of your vertical plane turn rate compared to your horizontal plane turn rate. So you'll essentially be able to approach that value that you have as a load factor as you're increasing that throughout the maneuvering flight envelope. Now, when we start to look at this from the standpoint of optimizing the performance of the aircraft for these various maneuvers, again, one thing we have to recall is all these pull-up and pull-down maneuvers considered have been instantaneous, really in contrast to the sustained maneuvers that we saw earlier. Now, for these instantaneous maneuvers, the thrust limitations that we see for things such as the banking maneuver aren't really relevant here. We have to think about these instantaneous maneuvers essentially being initiated by a very quick and sudden change in the lift when we increase the angle of attack for this maneuver to actually occur. Once this happens, we're also increasing the drag and therefore also increasing the thrust of the aircraft. However, once we do this, once we increase our angle of attack and increase that drag, that aircraft is suddenly going to experience a deceleration then. So this maneuver then really kind of provides us a limit as where our aircraft is going to have the capability to be able to maneuver. And so it provides us a way to look at the optimal performance for things such as a minimum turn rate and maximum turn radius for our aircraft. So in this case, we can make some simple substitutions looking at the load factor. And rather than writing this in terms of the overall just simple load factor and velocity of our aircraft for that given velocity, we could think about this in terms of the limit of where that maneuver is going to occur at which is that CL max. Again, this is that corner velocity portion that we have within our Venn diagram. So thus, for a given aircraft, if we know what the wing loading is and the maximum lift coefficient is, we can determine what that minimum turn radius is going to be as well. And this then gives us a bound for that aircraft performance in terms of trying to design for, that maneuverability piece of our aircraft flight. But again, we also have to make sure that this bound fits within the structural design limitations of our aircraft. Now, once you do this, you actually end up with some pretty interesting results, such as, which one of these aircraft has a tighter turn radius or a higher turn rate. You might look at these and think, oh, my modern fighter aircraft, the F-22, is obviously going to, it's designed for maneuverability, designed to be a fighter aircraft. It's obviously going to have a tighter turn rate and a faster turn radius. Well, not really according to the equations. All things being equal, assuming that the aircraft, say, have similar CL maxes, the wing loading of our Wright Flyer is much, much lower than the wing loading for our fighter aircraft. So this is going to dictate that essentially our Wright Flyer is going to be able to turn circles, within the larger turn radius that you have for the F-22. So you have to think about this in terms of the overall requirements that you have. And some of these results may be a little non-intuitive in terms of the capability. Now, when you look at the overall turn rate, however, velocity now comes back into play. And so even though the Wright Flyer can turn much tighter turns to its very, very low wing loading, the F-22, with its much, much higher velocity, is still going to be able to turn very, very fast. It's just going to have a much, much larger radius that it's turning around. So here's an example looking at the F-16 versus the F-4. You can compare, both the wing loading on the aircraft as well as the overall control capabilities and determine, which one of those is which. And you can think again about this in terms of a maneuvering requirement that you have for a fighter aircraft. The ability of the aircraft to be able to perform very tight turning maneuvers and essentially have the capability to get behind the other aircraft is obviously very, very important in an air superiority fighter. Now, the last piece that we're going to talk about this in terms of maneuverability is going to be what we call the specific excess power of the aircraft. When in reality, we've already looked at this at the rate of climb, because that rate of climb was looking at the excess power acting on the aircraft. However, when we examine this from rate of climb calculations, we were assuming that all of that excess power is going to increasing the altitude of the aircraft. Obviously, if you have excess power left over, which also means you have excess thrust left over your aircraft, you can do things other than climb. You can also accelerate. So now the general form of this equation, the excess power equation, is PS is going to be equal to the rate of climb of the aircraft, dH dt, plus also a term related to the acceleration of the aircraft. So now given what we call a specific excess power, remember we defined this in terms of the weight of the aircraft. Okay, now we're looking at this in terms of the specific excess power of the aircraft. You can determine how much of that excess power you want to go to increasing your altitude and how much you want to go to increasing the velocity of your aircraft. So instead of defining these in terms of contours or rate of climb, now we define these in contours of excess power. And then this excess power can then be distributed amongst those, two areas, either increasing potential energy or increasing your kinetic energy of the aircraft. So you really have this flight envelope then that anywhere within this specific excess power bound of 0, the closer you get down to the lower altitudes and a maximum value of specific excess power, the more you have to distribute amongst these different areas. Now, another piece of this then is the energy height, which is just the altitude that you have of the aircraft plus the kinetic energy. And you can think about this as a higher energy height of the aircraft is going to be a balance of the potential energy that you have, meaning elevation, plus how much kinetic energy you have. Because the faster you're traveling, if you stop putting energy into your aircraft, you can still take some of that kinetic energy and use it to increase your potential energy as well. So then it becomes the bounds of these two that allow you to determine what your overall really maneuvering capability of the aircraft is going to become. So as an example of this, you're able to take this specific excess power equation and then distribute it amongst different pieces. So let's say we have a maximum rate of climb of aircraft of 3,600 feet per minute, and we have a DVDT of 13 feet per second squared. In this case then, using these two equations, we can find both the specific excess power and the energy height for our aircraft at a given altitude and given speed, just by plugging those numbers in. Now, this, again, you can think of as an overall flight envelope for your aircraft, but the important piece to think about here is now that you have the capability to calculate separate contours for your specific excess power, at any one of these contours you can determine what the limits of your maneuverability are going to be. And then from that, determine things such as maneuverability diagrams. So given the energy that you have for any given maneuver, it's going to take a certain amount of energy, whether you're increasing your velocity, turning. And so it's not just a matter of load factor, but it's how much total energy you have capable or usable for that particular maneuver for your aircraft. So this now allows you to generate what we call maneuvering contour plots or carpet plots for your aircraft that tell you for any given velocity and any given load factor that you want to be able to impart on your aircraft, assuming it's under the structural limits that you have for your aircraft, you then can determine what that specific radius, bank radius, and bank rate is going to be for your aircraft. So in this particular example, let's say we're traveling at 400 knots and we want to turn at 10 degrees per second. That's going to require then at this point that we'll have to pull somewhere around 3.5 G's, and we'll be able to do this with a bank radius of 4,000 feet. So as I mentioned, this is really just kind of one small piece of the puzzle in order to be able to determine what these unsteady performance design requirements are going to be for our aircraft. We really want to start to look at things such as maneuvering capabilities for our aircraft and how we go through specific maneuvers. There's a lot that we still need to know that we don't understand yet. Some of this is going to be from stability and control, which we're going to talk a little bit about so that we would start to get a better understanding of what those design requirements are for, but we've really only scratched the surface. And so you'll see a lot more in stability and control next fall.